Hello, students. So today I'm going to be making this little video kind of going over a little bit about the basics of buffers. Some of this, hopefully most of it, will be a review from general chemistry and maybe even a little bit from organic chemistry. But since we have our lab prior to actually getting into buffers in chapter 2, I wanted to make sure we had a rather recent review on buffers. So today I'll be talking about what is a buffer, what do buffers do, and how do you make a buffer, since that is what you will be doing in lab on Tuesday. So what is a buffer? A buffer is an aqueous, water-based solution that resists change in pH upon the addition of an acid or a base. Now, a buffer resists change relative to an unbuffered aqueous solution, relative to water. This does not mean that there is no change when an acid or a base is added to a buffer. It just means this change is significantly less than we would see with an unbuffered solution. So how do buffers work? A buffer consists of a weak acid, proton donor, we'll call it HA, and its conjugate base, a proton acceptor. When an acid or base is then introduced into the buffered system, the ions from the acid or base, either an H plus if it's an acid or a negative OH if it's a base, are absorbed by the buffer and the pH remains stable. Okay, so if you kind of look at our two examples in our little illustration down here, if going to the left, you add an acid, the acid, rather than reacting with water, can react with the conjugate base, the proton acceptor that we have in our buffer system. If you add a base, if you look to the right, the base, rather than reacting with the water, can react with the weak acid we have in our system, and therefore nothing's reacting with the water immediately, and so nothing is changing the pH of our solution as long as we have sufficient amounts of that conjugate base and conjugate acid in our buffer system. Okay, so who cares, right? Why are we doing this? Well, that's a great question. So as we will see throughout chapter 2, our bodies are aqueous buffered systems. Whenever we do an experiment, you will be seeing that we are using buffers because nothing actually happens biologically in just water. It's always happening in a buffered system. And this is really good because we eat and drink things that are basic or acidic all day long. I'm going to show you in the next slide some of those things that we ingest. Plus, on top of that, we have biochemical reactions that are happening in our bodies that are making acids and bases all the time. Our protein structure and function are very depending on having a suitable, steady pH, and there's actually a very limited pH range that you and I can exist in. So we need a buffered solution. And looking at this chart, you can definitely see that there are quite a few things that fall on the acid-base scale that, you probably take in every day. We've got carbonated beverages, sodas, vinegar, orange juice, beer and coffee. These are highly acidic compounds that I know I drink on a regular basis. So it's really necessary that we have a buffered system to keep our pH from going out of whack. So how do I make a buffer? Since that's what we'll be doing today, we're going to go through one of the ways in which you can make a buffer. Now, you will see when we get to chapter 2, there's actually many different ways that you can go about making a buffer. Today, we are going to be making an acetate buffer, okay? And remember, since buffers are made from a weak acid and its conjugate base, the first thing that we are going to do to make our buffer is make equimolar concentrations of our weak acid and our conjugate base. Okay, so you're going to make a 0.2 molar solution of sodium acetate trihydrate. Okay, sodium acetate trihydrate. And you're going to make a 0.2 molar solution of acetic acid. Well, how do you do that? Okay, well, let's go back to general chemistry and remember our kind of units and our math. Molarity is moles per liter. To get how many grams you need to add to a volume to get a molarity, you would simply multiply the molarity of the solution that you want times the molecular weight of the compound you are doing. For our purposes, that will either be sodium acetate trihydrate or your acetic acid, times the final volume that you want of that solution. Now, all of those numbers, again, I said the molarity is going to be 0.2 moles per liter. The final volume of how much you're making is in your lab handout. You can find that easily in there. Your molecular weight, you're going to want to look up, okay? And again, this will give you how much you need in grams to make the solution at the molarity you want and in the amount that you want. Now, if you are using a liquid rather than a solid that you can weigh out, simply multiply the amount in grams that you got doing the initial calculation by the inverse of the density of the liquid. Density is generally given in grams per milliliter, so the inverse is milliliters per gram. Okay, to make your acetic acid solution, acetic acid is a liquid, so you will need to use its density to figure out how much acetic acid you're actually adding to make your 0.2 molar solution. Okay, now that gives you equimolar concentrations of your acid and your conjugate base. Okay. But that's not what we're making. That's not our final product. Our final product is a buffer. So how do we know how much of our conjugate base and our weak acid to add to make our final buffer? Well, we use our favorite equation of all time, the Henderson-Hasselbalch equation, which is, of course, pH equals pKa plus log of the concentration of conjugate base over the concentration of weak acid, okay? So we know that we want a buffer with a pH of 5. The pKa of acetic acid is 4.76. You should be able to figure out this equation and get the ratio of how much conjugate base to weak acid you need. Okay, once you have that ratio and you know what your final volume of buffer should be, you can use some simple math in algebra to figure out how much of each one of those two stock solutions we made you need to add together to make your buffer. Okay? Okay, so for the lab, you need to read the procedure and have an outline in your notebook, okay? You should have all of the math done, and I'm gonna check it before you start. You cannot start until I see your math. You should at least have gotten through the Henderson-Hasselbalch equation and solved for that. If you get a little tripped up on the algebra going forward after the Henderson-Hasselbalch equation, I'll help you out, but you should be able to get through there by yourself. I know you're going to be working alone. You got to wear the mask, face mask, visor, goggles, and gloves at all time. If you need to leave the classroom to get a drink or to go to the restroom, please take your gloves off and get a new pair, okay? If you have a question, please raise your hands and I will come to you. And if you break something or have any other concern or problem, just raise your hands and I will come to you. See you all on Tuesday.